All right, chapter 3. It's equilibrium of a particle. Who can recall Newton's second law? Ready, set, go. Newton's second law. You know, like the back of your hand, Newton's second law.
F equals ma.
Yes, thank you. F equals ma. Very good. Lucky for you, in this class, nothing is accelerating. Woohoo! All the civils are like, yay, nothing's moving. Mechanicals are like, let's get going. Things need to start moving, right? Okay. Hence why I love statics. I hated dynamics. I did all right because I went to the tutoring, but I hated dynamics because I don't like things to move. Nothing's moving in this class. Woo! Or if it does move, it's moving at a perfect constant rate so that acceleration is 0. Okay? So in this class specifically, acceleration is 0. Of course, if the particle is at rest, which most of the case in this class it is. Also, like I said, or it could be a constant velocity. So because the acceleration is 0, that means mass time acceleration is 0, right? Zero product property. So sum of all the forces in this class must add up to 0. This is like one of the key principles here of statics. So in equilibrium, all the sum of all the forces had to add up to 0. So this is all the forces acting on the particle. They all add up to 0. And this applies to all components. So this applies to both, you know, sum of the forces in the x. They all have to equal 0. And sum of the forces in the y. They have to equal 0. Okay, so let's define a few things. Let's talk about springs. So if you have a spring and some sort of force is pulling on that spring, the spring's going to become elongated, right? So it has some sort of original length, and then it has some sort of final length. So L naught for original length, S for how much it was stretched out. And just L for final length. So of course the final length is equal to the original length plus how much it was stretched. Or you could look at it like how much it was stretched is equal to the final minus initial length. And this could be positive or negative, meaning it could be compressed too, right? So if S is negative, force was pushing, right? Because it compressed it instead of pulling. So if it's pulling, it's going to elongate it. It'll be positive. If it's pushing, it's going to compress it. It'll be negative. And then as you remember, F is equal to Ks, K being the stiffness coefficient. And the stiffness of the spring is what affects the deformation, how much it's going to deform. So hopefully that's kind of a little bit of a review from physics, right? It shouldn't be brand new to you. But any questions at all about this, what the letters mean, stiffness, elongation, compression, any of that?
For S, it says if that says negative, right? Force was
negative.
Pushing.
Mm-hmm. Yeah, so if S was negative, that means it was compressed, so it got smaller, not longer. So because it got smaller, that means that the F was pushing on it, versus if the F is pulling on it, it'll get longer. Other questions? What's L naught? That's the original length. No, original length, OG. Yeah. Other questions? Let's talk about cables and pulleys. So you have this fixed support and you've got this pulley system. Where there's this like cable going through it. T for tension. So tensional force is something that is pulling. You'll notice cables are really good at pulling on them, right? But they're awful at pushing. Cables are just going to do nothing when you push on them, right? They're not going to be any helpful. They're not going to support much compression at all. So cables do not compress. You wouldn't use a cable to try and support a compressionary force, only a tension force. What's cool about cables and pulley systems is that if it's the same cable, if you can trace the line, it's the same string, right? Then it's the same force going throughout. So this is similar to when you go and work out, right, at the well, and you're lifting the weights with the machines. You see that pulley system going through, and you've put like the little pin in for which weight you want to lift. The weight throughout that pulley system, the cable is going to be constant throughout. So T is constant. throughout the length of the cable. Questions about that? Okay, let's talk about normal forces. Let's say we have an inclined surface. Let's say there's some sort of thing resting on the surface. It's being held up by like some tensionary force. At some sort of angle from the vertical. Let's say this is a 20-degree angle from the vertical. This is a 30-degree angle from the horizontal. Normal forces are always perpendicular to the surface at the point of contact. What I mean by that is if I were to look at this ball or whatever it is that's resting on the surface, it has a tensionary force holding it up. It also, of course, has its weight going down. And it's going to have a normal force in this direction because it's always got to be perpendicular to the surface. So because the surface is inclined, so is that normal force. So typically, if the surface is flat, like perfectly horizontal, right? You're going to have something resting on the surface, and therefore you're used to the normal force pushing straight up on it, right? The normal force always pushes straight up against that horizontal surface. Now, the thing is the horizontal surface rotates, and so does the normal force. It's going to rotate with the surface because it has to stay perpendicular to that surface. So if the surface is horizontal, okay, the normal force is perfectly vertical. But if the surface inclines, so does that normal force. It travels with it. Okay. Now looking at the original normal force being up, straight up and down, and the new normal force on that incline, do you see that angle that it rotates? The angle that the normal force rotates from vertical to inclined is the same angle that the horizontal surface rotates from horizontal to incline. Yes? From horizontal to incline is the same angle that the normal force rotates from vertical to incline. Same angle because they travel together. So the angle between the weight, which is always up and down, no matter where the surface is, gravity always pulls it directly down. The angle between the weight and that new normal force that is tilted because the surface is tilted is the same incline as the inclined surface, the 30 degrees. So of course the weight is directly down no matter what. The normal force could be directly up if the surface is horizontal, but if it's not, it rotates with the surface and stays perpendicular to that surface. And that rotation angle from the vertical to the new normal force is the same rotation angle as the horizontal traveled from horizontal to inclined up. Questions about that? So you'll notice what I did just now was I kind of simplified that diagram. And what we call those are free body diagrams. What free body diagrams do is they simplify diagrams. And what they're doing is they are freeing the particles from their surroundings. So if you're at the gym and you have this weight and maybe it says 5 kilograms and you have something that's like holding it up. Instead of having to be an artist, you would just say, I'm going to draw my plate as just a dot. And I'm going to draw all the forces acting on this dot. So for example, I've got the tension of the cable holding it up. I've got the other tension of the other cable holding it up. And what else is acting on this plate?
Gravity.
Gravity. So I've got the weight acting directly down. And weight is equal to what?
Mass times gravity.
Very good. And what is our mass?
5 kilograms.
And what do we multiply by?
9.8.
9.81 meters per second squared. Okay, so instead of having to draw the actual plate, you can just kind of draw a dot and draw all the forces acting on it.
So, Professor, we don't convert the kilograms
To what?
to pounds or something.
No, it just depends on the problem. Yeah, if it's in SI units, just keep it in SI units and vice versa.
Okay.
Like, let's say I had this crane. which is holding up a box. I'm going to free that crane from its surroundings by sort of cutting it out of the picture. And looking at the box by itself as just a dot. What forces are acting on that box?
Gravity and tension.
Very good. Gravity down, tension up. Make a note to yourself that these are not optional. The drawings, they are necessary in this course.
The whole drawing or just like the dot?
Just the dot.
Okay.
The original drawing should be given to you in the problem statement. And so you changing it from that to the dot with all the arrows is what I'm looking for. Now, it can be helpful for you to draw the original drawing, just like have it on the paper for you in reference to see how you went from this to that, you know? But in terms of the requirement, it's just that free body diagram with the dot. So for example, if, let's say I had like 2 inclined surfaces with like 1 kettlebell resting on both surfaces. And it's being held up by this string, which is then connected to a spring. Which is then connected to a pulley system. And here's the horizontal surface. So the inclines are both 30 degrees. Let's label this surface A and surface B. And this angle right here from the horizontal is given as 60 degrees. What I want you to know is it really depends on where you're looking. So free body diagrams depend on where you focus. So if I want to look at the kettlebell specifically, then I'm going to draw a circle and snip the picture just around the kettlebell. So I'm just going to draw a circle around the kettlebell only and figure out what did I cut through. to free the kettlebell from its surroundings. So the dot being the kettlebell, what is acting on the kettlebell?
There's tension B going to the right, then tension A going to the left.
Okay, so those are surfaces. So it's resting on a surface.
Oh.
A and
Oh,
B.
then it's just a tension on the top.
Yeah, so just the tension up. Okay, what else is acting on the kettlebell?
Is gravity also acting on it?
Uh-huh, the weight down. What else is acting on the kettlebell?
The pushing force on the right wall and
Very
the pushing
good.
force on the left. Yeah.
Perfect. So you've got a normal force up and to the left to counteract that right surface, right? So NB, we'll call it, for the normal force of surface B, and the normal force of surface A as well. What is the angle between the weight and the normal force A? What is the angle between the weight and the normal force B? Yeah, did you have a question?
Yeah, I have a question about like the arrows. So do they like, does it represent like, so do they have to be like equal, like the tension and the gravity, or like to define like which one is a bigger force or has a bigger tension or whatnot?
You mean like to scale?
Yeah.
No, they don't need to.
Okay.
Yeah, as long as, like, if you were to tell what these numbers were, you just label them with, like, okay, the weight is 250 pounds and the tension is 500 pounds or whatever it is. As long as you label the numbers, it doesn't have to be, like, to scale or anything.
Okay. All right.
Good question. Other questions so far? Now, what if I wanted to draw the free body diagram of just the cord? So this is the kettlebell. And what if I wanted to do just the cord? So what I mean by that is, instead of cutting the kettlebell out, you're going to cut only the cord out. So you're going to zoom in. You're going to say, just cut only the cord out. The cord is now your dot. What forces are acting on the cord?
There's a downward force from that kettlebell.
Basically, it's the tension of the string. Yes, the tension of the string is created by the kettlebell, but the kettlebell is not in the picture, right? It's just the string. So it's the tension of the string going down and up. And it's the same tension because it's the same string. Now, if you were to draw a free body diagram of the knot, so what I mean is that overlap intersection where everything is. So instead of the string, you want to focus on the knot where everything is connected right here. Now the knot is your dot. What forces are acting on the knot?
There's a force going down, the tension going down, and there's tension to the right. Or no,
Okay,
it's up. It's directly up, right?
Well, we've got the force of the spring going directly to the right. And then what else do we have? The tension. Yes, the pulley to the left. This way, like up and to the left. So maybe we'll just call it like T2 because it's a different tension than T1, right? And that T2, what angle is that at?
60.
Very good. So you see, it does matter a lot what you're drawing the free body diagram of. Are you drawing the kettle? Are you drawing the string or the cord? Or are you drawing the knot, right? It depends. But the key is that you always just want to isolate your particle, whatever the particle might be, from its surroundings. And only show the forces that are acting on that particle. Don't include anything else that you didn't cut through. Only if you cut through it, you would include it.
I have a question, Professor.
Mm-hmm, mm-hmm.
So, you know how you drew the knot and it says the force going to the right? So why is it like, how do you differentiate between the force and then the tension?
Because the one going to the right is a spring. So that's a spring force. And the pulley going up and to the left, that's a totally different. That's like a cable system. And the string going directly down is what's holding up the kettlebell. So each three of those are totally different forces acting at the knot.
So whenever we see a spring, it's technically a force,
Yes.
not a tension.
Yeah, well, it's just to differentiate it. It's a spring force. Now, it could be tension or compression, right? Because the spring can pull, but it also can push. It just depends. So regardless, we'll just call it the force of the spring.
Okay, got it. Thank you.
Yeah. Whereas if it's a cable or if it's a cable, then it's definitely going to be only tension. It can't be compression. But a spring can either be tension or compression.
Thank you, Professor.
Mm-hmm. So we're going to do an example. So this is a second example of the lecture, and it says to determine the tension in cables BA and BC necessary to support the 60-kilogram cylinder. So we've got a cylinder. You get the idea. I'm just gonna undo that. Okay. A cylinder. And it is being held up by a string that is connected to a ring. And that ring is connected to a support over here and also connected to a support over here. And this is like hooked on to a wall. Hooked on to a wall. Cool. All right, so this is point A. This is point B. This is point C. We'll call this point D. What the heck? I don't know what my notes mean right there. What does that mean? And then we are given the slope here is a 3, 4, 5 angle. Three, four, five. And we're given the angle here is 45. Got it. Okay. So first thing we're going to do is cut out D from its surroundings. And we're going to draw a free body diagram for point D. So drawing a free body diagram for point D, what forces are acting on D? W. Very good. Good. And instead of just T1, I will label it with the letters. So I'll say tension in string DB. Okay. How do you calculate the weight? mg. So what's m?
Kilograms.
And what's g?
9.81 meters per second square.
Very good. So what do you get for the weight?
$588.6.
Units? Newtons. Okay. Yes.
Professor, I have a question. So basically, if B didn't have that little circle and it was just those two ropes attached to the bottom rope, would it be tension 1 and tension 2?
Well, you have a tension from B to D and a tension from B to C and a tension from B to A because they're all 3 different strings connected to a ring.
So there's 3 tensions, correct?
Yeah, there's 3 different tensions, but
Okay.
point D is not connected to those other 2 because we're isolating it. We're cutting it out from its surroundings. So that's what that purple dashed line is. And the question is, what did we actually cut through when we cut it out of its surroundings? We only cut through that one string from D to B.
Oh, okay. That's what I was confused about. Okay, got it. Thank you.
And so now, and don't say I never told you this, set up your sum of the forces in the y direction, positive being up. Everything has to equal 0 if it's in equilibrium. Okay, so even though you can look at this maybe and intuitively know that and feel like you don't want to write that on the page, That's a good way to get 70% on a quiz instead of 100% on a quiz if you don't show your work. Okay? Show your work, even though it seems like, well, I just thought about it in my head, so why should I have to write it down? Show your work. This is how you show your work. This is why it's open book, open note, right? Take good notes so you see what I want you to do and then do it on your homework and your quiz and your exam. Okay. So some of the forces in the y direction, positive being up, everything should equal 0 if it's in equilibrium. So we've got T dB. Is that positive or negative based on our convention? Up, positive. T dB is pointing up, so it's positive. And how about W? Is that positive or negative based on our convention? Negative because it's pointing down. All of that should equal 0 if it's in equilibrium. Add W to both sides, you get T dB is equal to W. Therefore, T dB is equal to what?
588.6
Okay, so this is my exact point. You might be able to look at it and know that the tension in the string must be equal to the weight by intuition. And you might be able to look at it and say, therefore, the tension in the string must be 588.6 newtons. Okay, but show your work on really how you got there. This is really how you got there. T up, W down equals 0. Solve for T. Okay, that's how you show your work. Questions about that so far? Okay, so Mr. Singh, I think this will answer all your questions now, because what if instead of doing a free body diagram for point D, we did a free body diagram for point B? So now you ask yourself, what did I cut through to free point B from the diagram? So freeing point B from the diagram shows other things going on. So if we have point B here, what's acting on point B?
The tension from A to B and C to B.
Very
and
good.
Also B to D.
Yes, very good. So in tension, you're always going to draw outward because it's a pulling force, not a compressionary force. So you always draw outward from that point. So we can label this as T, BA. It doesn't really matter if you put what letters, but for me, I just like to start with the origin and go out. And then T, BC, and T, BD. Okay, and then remember to also label the slopes. So you've got from here, and then remember they gave you this slope too. So you've got 45 angle here. You have a 3, 4, 5 angle there. Questions about that free body diagram?
I have a question. So you know how you put TBD?
Mm-hmm.
So if we necessarily weight is technically is it a tension?
No.
Okay, so if we had put weight there, we would get it wrong, correct?
I would say so. So technically TBD, we just proved that TBD is equal to the weight, but that's only in the sense of the magnitude, essentially. They just so happen to have the same magnitudes, but that is not the weight. So the weight is the force acting on the cylinder, which is pulling down, right? The tension is the force holding it up in the string. And we didn't cut through the weight of the cylinder when we looked at the ring. We cut through the string. So therefore, it's a string.
So it would be weight if there's an object pulling on a string, basically.
Exactly. Yeah.
Yeah. Okay.
Mm-hmm.
All right. Thank you.
Yeah. So let's see. We can do sum of the forces in the x direction, positive being to the right. If it's an equilibrium, everything must equal 0 in this picture as well. So in the x direction, what do we have moving on in the x direction? What's going on in the x direction?
We have the x component of TBC.
Very good. And how do we find that?
We do cosine of 45.
Very good. TBC, cosine of 45. What else do we have? And first of all, is that positive or negative?
It's positive
Why?
because going to the right.
Very good. And how about TBA? How would we find the x component of TBA?
That's just cosine. Oh no, it's 3, 4, 5. You do. Can you do tangent inverse to get the angle?
You don't even need to. It's going to be just like the same ratio of the horizontal over the hypotenuse. So what is the horizontal component in that little triangle they gave you?
Oh, it's 4.
So you're going to say it's going to be the same as 4/5 because essentially that is cosine, right? Cosine is adjacent over hypotenuse. So it'll be the same ratio as adjacent over hypotenuse of the slope of the line, 4/5. It's just reduced basically.
And then would it be negative?
Exactly. Yes, it's negative. Why?
To the left.
Pointing to the left. Very good. And all of that must equal 0 if it's in equilibrium. Questions about that setup? We can look at the exact same diagram and do some of the forces in the y direction. So let's just keep this clear. These are two different situations. So sum of the forces in the y direction, positive being up, everything should equal 0 if it's in equilibrium. Help me set up the y components. What do I do?
So you can do TBC sine of 45.
Positive or negative?
Positive.
Good. What else?
And then TBA 3 over 5. And it's
Positive or negative? Good. What else?
And then TBD, negative TBD. Because it's going down, so it's negative.
Perfect. Questions about that? Now, we do already know what TBD is. TBD we solved for in the other diagram. We know it's 588.6 newtons. We can rearrange some variables here, like for TBC up on the sum of the forces in the x direction. So if we wanted to solve for TBC in the sum of the forces in the x direction, we could isolate the variable. So for example, I could add TBA 4/5 on both sides, right? And then I could divide by cosine 45. And so I could actually say that TBC is equal to, let's see, TBA times 4/5 divided by cosine of 45 degrees. Questions about how I got that? And when you type that into your calculator, you can write, it's basically, because cosine 45, you can write 4√2 over 5 TBA. So this is just algebra, right? Because at this point we have two equations and two unknowns. So I'm isolating a variable so that I can plug it into the next equation. So I can only have one variable, right? So two equations, two unknowns, systems of equations, right? So I'm doing substitution as my solution. So I'm substituting in this into TBC now, which is good because now it's going to be all in terms of TBA. So we've got 4 root 2 over 5 TBA times sine of 45. So I just did substitution right there. Plus TBA times 3/5. Minus 588.6 newtons, all equals 0. Okay, consolidate all the TBAs. So you've got this added to that. What do you get? How many TBAs do you actually have when you add them together? Combine like terms?
You asked how many TBAs we have?
Yeah.
Oh, 2.
No, you have a 3/5 of a TBA and a 4 root 2 fifth times sine 45 of a TBA. So add them up, and what do you get? How many real TBAs do you have? Combine like terms. What's the full coefficient in front of the TBA? You won't have your buddy to do the algebra for you on the quiz or the homework or the exam. So it's time right now to try and do it yourself and see if you get the right answer. How many TBAs do we have?
0.48 TBA?
Um,
What is that?
That's not what I got. Yeah, I got 1.4 or 7/5. If you were to use your calculator, it might keep it in fraction form. 7/5 TBA. And then I would add the 5.88 or 588.6 to the other side. So questions so far? How we got that?
What happens to the root?
So 4 root 2 over 5 times sine of 45. Do that in your calculator first.
Oh, okay. No, I thought you just added them the 4/5 and
Yeah, multiply.
Okay.
And then add the 3/5 and you should end up with 7/5.
Wait, if I do 4 root 2 divided by 5 and then add sine of 45?
No, multiply.
Oh yeah. If I multiply 4 root 2 divided by 45, I mean divide by 5, I could do that. I could do that before I multiply sine of 45, right?
You could, or you could do it all
Okay.
in one. Like you could put 4 root 2 sine 45 all over 5 if you wanted, because it's all in the numerator.
Okay, I see what I did. I added it instead.
Okay, yeah, it's all being multiplied, and then you add the 3/5. So you get 7/5. You add the 588.6 on the other side. Questions about what we're doing so far? It's just algebra. Okay, solve for TBA. What do you get?
420.4 newtons.
Very good. 420 newtons. Okay, so remember we already isolated TBC. It's 4 root 2/5 TBA. So what is TBC now that you can plug it in? So TBC is just 4 root 2/5 times TBA, but keep the number in your calculator. So what do you get for TBC?
I got 475.66 newtons.
Very good. Okay, I would say you can make a note here. If you have a TI-36X Pro, you can use system solve. So use system solve on your calculator. We just did the algebra, but learn to use system solve on your calculator because it might even get more complicated than that, and you don't want to waste your time bogged down by the algebra. So with system solves on your calculator, if you have the TI-36X Pro, the system solve button is above the tangent button. So if you hit the second tangent button, that's your system solve. And it asks you, do you have 2 equations and 2 unknowns or 3 equations and 3 unknowns, right? And we got it down to having 2 equations and 2 unknowns. The sum of force of the x, sum of force of the y. We use substitution algebraically, but you could just use your 2x2 matrix. So you could use a 2x2 matrix. All it does is it asks you for the coefficients in front of x and y. So you would assign x to be like TBA and assign y to be TBC, for example, and then bring all the other numbers like the 588 or whatever onto the right-hand side and type that in. So you just type in the coefficients, ax, by, c, ax, by, c, and it'll just crank it out and answer and give you both the answers all at once. So practice that at home. Your calculator can solve 2 equations, 2 unknowns for you, so you don't have to do the algebra. It can do 3 equations, 3 unknowns as well. So there are more examples. If you want to try more at home, I would suggest you can always come to my office hours too and like try and work on those examples. And that way I'll be there to answer your questions. But it's always good to try and do these things on your own because yeah, following my algebra might make sense because I'm doing it, but can you do it on your own? Do you know what the next step might be? So try examples 3.3 and 3.4 that are in the book on your own. I want you to note that these principles do apply in 3D as well. So you could do some of the forces in the I, you could do some of the forces in the J, and you could do some of the forces in the K, and all of those are supposed to equal 0. And if you're curious about how that works, you can check out section 3.4 in your book. Why does it do that? I can do it. There we go. Make a note that if you accidentally assume the wrong sense of the force, meaning you like drew the arrow in the wrong direction, it'll come out in the wash. Your answer will come out negative. And so that just means you drew the arrow in the wrong direction. So this indicates the force is actually applied in the opposite direction. That's all I want to cover for chapter 3. So had a question with when using cosine and sine. What location do we base it off of? So for TBC, we use sine of 45. Did you base the view on B? Yes, so we looked at this triangle right here. And so we said sine is the opposite over hypotenuse, so that's your y value, and cosine is adjacent over hypotenuse, so that's your x value.